SwayamPrabha. Digital India. Educated India.
Good morning everybody and welcome again to our course on mechanical introduction to mechanical micro machining. In the last class we started our topic on sensor and metrology for micro machining operation, and we have seen that there are different type of sensors which can be used for monitoring of the machine tool itself, monitoring of the workpiece and monitoring of the cutting tool. So, let us continue this topic further. So, last lecture we have seen that there are two different approaches by which you can do measurement of different type of signals. So, one is the direct approach and this one was the indirect approach. So, there are different type of measuring systems also. One is called continuous measurement. What does it mean? That means that you are continuously detecting the measurement signal, that is called the force signal, right. So, force signal we directly measure onto the workpiece or the cutting tool, and then because of that continuous measurement what we can detect, that we can detect sudden or unexpected process disturbance like a tool breakage or the response in the good time. So, if you measure something in a continuous operation, then what we can do, that we can actually stop the operation once you get some type of unwanted result or there is some type of problems in the system. So, that is the reason that continuous measurements are very useful in the real time monitoring of the machining operation. Another thing is the intermittent measurement, that you do a machining operation, then stop the operation and then you take out the cutting tool and then do the measurement. So, what we are doing here, that when you want to do these things continuous, then mostly we actually use a indirect approach, right, because we are measuring forces here. So, force measurement, right. So, force measurement is indirect approach, but what happens by measuring the force, actually you can find out the what is the tool breakage or anything, because suddenly decrease in the cutting tool cutting tool force signal, then what you can tell that there is a wear of the cutting tool or there is a sudden completely breakage of the cutting tool. So, by that way you can monitor continuously. But if you want to do intermittent, that you complete the operation and then take out the cutting tool and then you put that things under the microscope and then you do the all the studies. So, there is an interruption in the machining operation or you need a special interval in between these two. So, what are the consequence of that? You will end up with the time loss and the high cost, because you are interrupting the machining process and you need a separate station for putting all these things and then do the measurement. So, sometimes what happens, these things is important in some cases, that you do not have space available in the continuous operation, and ultimately what we are measuring, we already seen in the last slide, the force measurement is indirect measurement. So, ultimately you are end up with some type of equation calculation, and that everything depends on the how accurately you are putting those equation in terms of the fitting of the curve. But intermittent, what is the advantage, that you are measuring the actual quantity, but you have to stop the machine and then do the measurement. But this is more reliable, it will tell you the exact position of that. But we know that still people are using this thing because there are some advantages associated with the indirect measurement or the continuous measurement, that is not possible here, because ultimately you are end up with the time loss and the high cost, that will also create a very important role in the final production. Right. So, suppose you want to measure the tool breakage by intermittent measurement, it can identify only after completion of the machining cycle, right. So, you do not know that at which particular location your tool is broken and you still continue operation there, and finally, you cannot prevent the damage of the cutting tool as well as the workpiece part. So, that is the problem when you go with the intermittent. But there is a solution also. Suppose you are working with a automatic tool changer, then what you do, that you do not need to provide a separate interval for this particular operation, because whatever you are using here, what you can do, you do machining operation and then you change the cutting tool, and whenever you are putting that used tool into the tool magazine, then put a sensor there itself in the tool magazine. So, while going when you are doing a machining with another tool, by that time already used tool is being monitored by a sensor system, so that you do not require in depth of special interval between the machining. So, you continue that operation, and in the tool magazine you are actually doing all the analysis of the tool geometry, that what are the cutting edge available, whether it is a broken or it is a worn out. So, this is also one of the solution by which you can actually reduce the time loss. By that way you can still continue with the measurement of actual quantity, and still you maintain the production time without any problem. So, by that way you can actually find out there are different ways by which you can use the intermittent measurement, but still maintaining the production time. Now, coming to the sensor fusion. So, what is the sensor fusion? Now, what happens that when you use any type of monitoring system in terms of sensor or some type of metrology, everything actually depends on the how much it is reliable and how much it is robust, right. So, once you get a signal, you have to find that whether it is reliable or not, it is showing you correct results or not, and another thing is robustness. That means you are end up with a lot of different type of environment. When your depth of cut is very high or it is very small, how it will respond to your stimulation of the input. And we also know that none of the sensing systems are 100% reliable, right. So, what to do in this case is, so what we have to do, that use more sensors, either it is similar type or the different type, for making the monitoring system more flexible and reliable to detect the various type of malfunctions in the process, right. So, what we have to do, that suppose you do measurement with a one system, suppose you consider you are using a dynamometer, right. So, you do measurement with a one dynamometer and you use measurement of with a similar type of dynamometer, and then you check that what are the variation in the cutting forces, or you use a different one, you use a dynamometer, under you use a acoustic emission sensor, and then you compare the signal. So, in that way you can actually increase the reliability of the signal. So, now this particular graph will tell you many things here. So, what it is showing here, so this is the reliability and this one is the flexibility, right. So, this is a single sensor system. So, you are using a single sensor here and you are monitoring the system, that whatever process you are monitoring the cutting tool, or you are monitoring the workpiece. So, this is called the replicated sensor. Replicated sensor means you are using a similar type of sensor more than one to monitor a particular situation, and this is called a disparate system, sensor system, where what you are doing, you are monitoring or you are measuring a single quantity using a different sensors, right. So, these sensors are different and those are working in a different principle of measurement, and these are the similar kind of things, right. So, now what is happening, that you, if you use a different sensors with a different for measurement of the same quantity, then what happens, you are actually increasing the reliability of the measurement, because we know that if one particular measurement principle is not fitting with a particular system, then what happens, that if you are using a single sensor or you use a multiple sensor with a similar configuration, it will not make much difference there. But if you use a different sensors working on a different principle and they are all measuring the same quantity, then you have a large amount of database, and then you can see that whether your requirement or the whatever parameter you are measuring, it is showing the correct trend or not, and it also increases the flexibility. So, that is the advantage of going with the disparate sensor system. Now, this is the example of a diamond turn machining operation. Now, you can see here. So, this is the component, machine component, this is the chuck, and this is the cutting tool. So, what we are doing, we are using one force sensor here. So, if this force sensor will measure the cutting force, we are using one vibration sensor here also. So, that is also attached with the cutting tool. So, whether cutting tool is moving with a predefined depth or what happens to the cutting tool, it will measure. Then we are again putting one acoustic emission sensor. Now, you can see that all the three things we are putting on a cutting tool, and all the three sensors will give you a signal, and then you get a sensor fusion. So, by that way you are actually increasing the reliability of the system, sensor system, so that you do not end up with any type of wrong measurement or taking some decision based on the wrong measurement, right. So, what happens, that suppose you get the wrong measurement, you do not have any problem, because at least you understood that there is a problem in the system. But suppose you get one wrong signal and you are not able to identify whether it is wrong or right, and you take some decision based on the wrong signal, that will create more problem, because you do not know what happens based on the final decision, and you further do some type of wrong setting in the process parameter, and at the end you actually create some type of problem into the workpiece, and it will be rejected at the later stage. Right. So, what our objective that you use a different type of sensors for measurement of a same quantity, that will create more useful system for measurement of the different quantities. Now, coming to the dynamometer. So, dynamometer mostly we use with the force measurement. So, that is called the force are usually measured with the piezoelectric sensor called dynamometer. We use the strain gauge based load cell also, but we know that when you want to measure something at a micro scale, it is better to go with a piezoelectric type of sensor, because these things are very robust, and it is very rigid, because suitable for acquiring high dynamic signals, because even if you do machining at a micro scale, you have one particular range, micro range, by which you can do you can get the signals at the micro scale also. So, these are the one, this thing is called the rotating dynamometer, which is attached on the cutting tool, and this is called the stationary dynamometer, which is at the workpiece side. So, compact and robust, because these are ideal for the tough service condition, because we know that we are using coolant also, then we are using, there are a lot of chips available coming out of the workpiece, and those chips are actually fallen down onto the workpiece in nearby area. But if you are, so if your dynamometer is not able to cope up with this type of tough situation, then you cannot use it. So, this dynamometer based on the piezoelectric sensor principle or piezoelectric based type of sensor, then that is not creating any problem in the measurement part also. But there are different issues, that thing, the magnitude and directions also play important role, and those things are depends on the three main parameters: speed, feed and depth of cut. Because we know that by measuring or controlling these three parameters, most of the things you are end up with a correct measurement or correct component out of the machine. Rest of the thing, the cutting tool and the workpiece material, those things are the secondary parameters, but these three are very majorly play important role into the required quality of the component. What are the other components? One is the material, which type of material you are machining. Hard material will give you more signal, soft material will give you less signal. Coating of the cutting edge, that is also important, because when you do coating, what happens that you are increasing the life of that particular cutting tool, and by that way you can reduce the cutting forces. Cutting geometry is also the negative rake angle, positive rake angle. If you use cutting fluid, then you reduce the cutting heat effect, heating of the component on the tool side as well as workpiece side, and depending on your cutting tool signal will cutting force signal will change. What are the different type of dynamometers? One is called the stationary dynamometer. So, these are called stationary dynamometers. Stationary dynamometer means they are not in motion, and those are mounted on the machine table and workpiece on the top of that. Now, you can say this is the dynamometer. On the top, what you are doing? You are putting a fixture. This is the workpiece fixture, and workpiece is on the top, correct? And then you do machining, and then you will get X, Y, Z, or whatever force you want to measure from it. And this is the drilling operation. So, you want to measure the moment also. So, this is the 4 component dynamometer. Other than you are measuring X, Y and Z, it measures the MZ also, that is the moment around the Z axis. So, by that moment you can measure the torque also here. So, in that case, this is the 4 component dynamometer, both are stationary type of things. So, here it is mounted on the table and workpiece is on the top of it. Right. What are the application of this dynamometer? So, those applications are turning, milling, drilling, surface grinding. Wherever your workpiece is stationary, you can use it. By that way, you can put the, in turning also, what happens that in turning it is a different way, that you, when you want to use a turning operation, for that what happens, the dynamometer is not attached with the workpiece, because we know in turning operation workpiece is rotating, but cutting tool is fixed. So, there are some provision available where you can put your cutting tool onto the dynamometer and then you do machining. So, in that way it will give you a different results, right. So, another thing is the rotating dynamometer. So, rotating dynamometer, that means it rotates along with the cutting tool. So, this one is attached onto the tool side, not to the workpiece side. Yeah, so, this is the connection. In earlier case, what was the scenario, that we are using a dynamometer here, correct. There was a dynamometer on the top, there was a workpiece fixture, and on the top there was a workpiece, and then dynamometer was located here, but now dynamometer is located on the cutting tool side. So, mounted directly onto the spindle of the machine. tool and the tool is mounted on the rotating type dynamometer. So, this is the actual photograph of the cutting tool dynamometer. Right. So, here what is the it measured directly to the MZ torque. Now, earlier case what was the thing that you have to actually find out in terms of the where that sensor is located, how far it is. So, it is direct measurement of the cutting torque. Earlier that was not the direct measure, by moment you are measuring the cutting force, and measurement is very close to the cutting tool. Now, here that most of the times what happens that when you do measurement of cutting force by means of dynamometer, our objective is to find the status of the cutting tool. But if you see that stationary type of dynamometer, what was happened, the dynamometer was attached to the workpiece, but we want to measure the, or we want to get information of the cutting tool. So, it was distance was very large. So, here what is the advantage here, the dynamometer is very close to the tool. So, measurement is very reliable in terms of the rotating dynamometer compared to the stationary dynamometer, and no influence of the change of the mass of the workpiece. Now, if you see that earlier case, what was the thing, that this was the situation, your dynamometer was here, on the top there was a workpiece fixture and on the top there was a workpiece. Now, you are doing machining. Now, what happens that when you are you already have some type of preloading. So, this is called the loading of workpiece and fixture. Right. So, when you want to do measurement of a normal force, that is the Fn, what happens, your starting point is this one, right. Your force will start from here and then it will go something like this, right. So, this is the force because it is already loaded. So, this force is because of that, and now you do that, you are doing machining with a different depth of cut. Now, you want to do some type of 2 or 3 passes. So, one pass is done, second pass is done, third pass is done. So, what is happening, that this particular graph will always try to change and then it will come here. Right. So, this is the change of the, so whatever the mass of the workpiece, you always get a some different offset after each and every pass. So, what is the problem here? The problem is in the post processing. Here you will not get any problem because every time you know that this is going to happen, but ultimately when you want to do measurement of actual force is this one, from this to this. So, if every time it is starting from here, what happens, that you do not need to change the baseline, but every time when you do cutting of there this much amount of operation, then this much amount of material is lost. So, your graph will start from the little bit lower side. So, now actual graph is this one, in the third graph this is the actual graph. So, post processing require one additional step by which you can actually get the datum plan very effectively, but that is not a problem in this rotating dynamometer because dynamometer is located on the cutting tool side. So, whatever machining you are doing, you will always end up with this particular graph. So, this is the one graph, you start with the second graph. So, your datum will never change, and that is the advantage, that you do not require any type of additional step in the post processing of the signal. So, that is big advantage. Application is milling and drilling because these are the two operations by where you can mount a dynamometer onto the tool side. So, how do you measure? So, this is the stationary dynamometer and you can see that there are 4 different sensors available, and this is whatever direction is showing. So, these are the positive directions. If force is acting in this direction, that they are considered as a positive, and these are the 3 moments. This is mx, that is along the fx, my, that moment around the fy, and this is the mz force, that is the moment around the fz, and these are the distance from the center point. It is in the vertically these are located at bb, and horizontally they are located with the AA. So, how dynamometer measure this all the forces? Now, when it measures the force in the fx direction, so this is called the fx. So, this is your x direction, right. So, in x direction what it will do? So, it will do measurement of this part. So, this is the one measurement and this is the second measurement. So, this is the 3 and 4. So, this is the sensor 3 and 4 summation of these 3 2 forces plus sensor signals from the sensor 2 and sensor 1. So, this is the fx1 2 plus fx3 4. So, 1 2 plus 3 4, by that way you can find the fx force. Second one is the fy. So, similarly in that way. So, now your fy force is in this direction. So, this is fy. So, similar to that, now what you have to do? You have to do summation of this signal from the signal of sensor 1 and sensor 4. So, this is sensor 1 and 4 in the y direction. Similarly, it is a sensor 2 and sensor 3 that you are getting in a 2 direction, 2 plus 3 in the y direction. Now, coming to FZ, that means what we are doing here, we are actually loading from the top. When you are loading from the top, you understand that all these 4 force load or sensors will actually press simultaneously with a same reading. So, what we are doing here, that we are directly summing the Z1 plus Z2 plus Z3 plus Z4, because now all distances are same from each other and all will be loaded with the same value. So, it is a straightforward calculation. Now, coming to the moment. Now, what is this movement? So, now this is mz, mz, that means what we are doing, we are measuring movement in this direction. So, this part is the loading part and this part is the pulling part, right. We are pressing only this part. So, when you press this part, this will give you a positive reading and we are loading from the top, that means only z will be active direction. So, when you are loading on this direction, this will give you a positive reading. So, this is 1 and 2, right. So, this is the 1 and 2 are positive. And how far it is located from the sensor? These are located from the sensor with a B value, correct. So, this is the B value. When you are loading from this direction, then similar way you will get the pulling from the other side. So, when you are getting pulling, so that is called the 3 and 4 are negative. So, these are the 3 and 4 are negative, but both are also located with a B distance from the sensor, right. So, mz value you can calculate by this way. Right now, we can see that this is the movement around this part and we are calculating those things. So, earlier case we have seen that you can directly measure the torque in a rotating type dynamometer, but here you have to do calculation. Now, similar to y, how do we calculate the y? So, now this is the y. So, we are loading from this direction. So, these both things are positive now, right, because loading, we are loading on the sensor 2 and 3 side. So, sensor 2 is positive, sensor 3 is positive. These two are negative because now we are pulling from that side. So, this is called Z1 is negative, Z4 is negative, and how far those are located from the sensor? Both are located the sensor at a B distance. So, A distance, sorry. So, you are getting the A here. So, these all calculations are very straightforward if you know the moment and the force direction, but still one thing is left, that is called mz. So, this one is little complex. Now, this direction is this direction. Now, we are rotating in a clockwise direction, right. So, when you rotate in a clockwise direction, now what happens that we are not pressing the component, right. Earlier case whatever we are pressing, so everywhere you will see that these are the fz only comes into picture. But here in mz what we are doing, we are not pressing there, but we are actually shearing the plate. So, when you do shearing, then x and the y force will come into picture. So, let us first see the measurement of a different components. Now, when it is rotating in this direction, right. So, it is moving in this direction, let us see, and then it is moving in this direction, right. So, when you, let us consider first in the y part, right. So, this is the y part. So, when it is moving in this direction, now you can see this direction is aligned with this direction, correct. So, this 4 and 1, this will give a positive result, right. So, this is the Fy, that is 1 and 4 are positive, correct, and how far it is located from the sensor? They are located from the sensor at a distance. Coming to this direction, it is moving in this direction. So, this direction and this direction are opposite to each other, right. So, if sensor 2 and 3 in the y direction, you will get a negative. So, here this is what is happening, that 2 and 3, but they are negative, and how far it is located? They are located with a distance, right. So, this part is over with respect to y. Now, let us talk about the z, x. So, now still it is rotating in this direction. So, if it is rotating in this direction, what is happening, that it is moving in this direction and then it is moving in this direction, correct. So, now you see that direction of x force is in this direction, but now you are moving in this direction. So, 1 and 2 will be negative, right. So, 1 and 2 are negative. How far they are located from the center point? They are located at a B distance. So, this is the B distance, and then you are on this direction, this is in the movement is in this direction, your force direction is also in this direction. So, sensor number 4 and sensor number 3 are positive, and both are positive, both are located at a B distance. So, this is a B distance, right. So, you can see that by this way you can do measurement of a cutting force in XYZ direction and then movement in the XY and the Z direction by this type of calculation. But you do not need to do this calculation. This calculation is done by the software, whatever interface you are providing. Ultimately, whatever final you will get a graph only. So, you do not need to worry about it, but you should know that what thing is going on inside the sensor, so that you can find out the any type of relation if you want to do measurement by a manual calculation also. Right. Now, coming to the acoustic emission sensor. Now, each and every sensor you can also take as a separate course, but we are right now what we are discussing a small amount of introduction only, then only we can cover all these things into the this course. So, acoustic emission also is one of the sensors which is widely used for micro machining specifically, so that you can get the reliable signal similar to the dynamic dynamometer. So, what is the acoustic emission? The acoustic emission refers to the generation of a transient elastic wave produced by a sudden distribution of stress in a material. Now, you can see this is one of the component, and here some disturbance has happened at this location at source. Now, what happened because of that disturbance, what happened that there are stresses generated in a different direction, and there is a acoustic emission waves which are created from this location. So, if you put one sensor here, that is called acoustic emission sensor, our objective is to capture this particular elastic waves, so that you can get a signal and then you can do some type of post processing or the decision making based on this sensor. Now, wherever you will get some type of disturbance into the material, or when you get some type of stress generation there because of the stimulation, you will get one signal because of the acoustic emission wave. So, this based on this principle, this is very useful sensor for specifically in the micro machining domain. So, structure is subjected to an external stimulus, change in the pressure, load, temperature. Because of that, you will get a different type of signal here, and localized sources triggers the release of energy in the form of stress waves. So, whenever you will get this type of disturbance here, it will generate one type of energy in the form of stress waves. So, that is what we call as elastic emission waves, and which propagates to the surface, and then it is recorded by the sensor. Now, it is like that suppose your sensor is located here and your disturbance is here, then there is a chance that you will get a very reliable signal, because disturbance is located very close to the sensor. Now, if it is very far away from the sensor, then what happens that when it travels to this part, then everything depends on the material property, how far your material is able to transfer that particular wave to the sensor location. So, location of the sensor also play important role, where you are putting the sensor, and if you know the location of the deformation. And we know the, if you do machining, we know the maximum deformation takes place at the tool and workpiece interface, but we know that is also know that it is difficult to put something there. So, we have to put sensor, any sensor, let it be acoustic emission sensor or the dynamometer, we have to put those sensor as close to the machining condition to get the reliable signal. So, what are the different type of components of the AI system? This is the cross section or the cut view of the acoustic emission sensor, and these are the sensor. It is something like a cylinder. So, here what things are there? It is a sensor housing, because you have to put housing so that we can use this thing in a very harsh environment when cutting fluids are there and cutting chips are also available, separated here and there. Piezoelectric sensing element is available, that is by which you can do sensing element, and inbuilt impedance converter available, because you have to reduce the opposite flow of the current, so that it will not create any problem at the signal strength. Sensing element, mostly it is a zirconiate titanate, that is called the piezoelectric ceramic is used, and it is mounted on a thin steel diaphragm. And mechanical strain of a piezo element generates the electrical signal. So, here also you will get electrical signal in terms of voltage, and then convert that voltage in terms of a required quantity or whatever parameter you want to measure here. So, important thing here is that how you are putting this particular or installing this particular sensor here. So, that particular sensor installation is very important here, because now if you see this is coupling. Now, if you are not completely fitting or completely installing this acoustic emission sensor to the sample, if there is some air gap, then what happens? You are losing some energies there, and that is the big problem. and let us see this particular last thing also. So, this is what it is showing. So, here you have installed a sensor here, there is some disturbance here, or you are putting some type of loading here, and that disturbance will create some type of waves, and that waves are created captured by the sensor. So, this is the rough signal here, and you have to amplify it, because amplifying is required, because we know that when you do some machining at a micro scale, the strength or the magnitude of your signal is very small. So, to make it more readable, what you have to do, you have to amplify that signal, and once you amplify that signal, now you can see that different components you can easily identify. Then acquisition and data acquisition storage system available, by which you can actually do some type of signal processing and then storage of data, and then you transfer to the computer screen where the software is available, which will do all the different type of curve fitting related to the signal. So, by that way you can do lot of measurement of the signal, and this particular what we are discussing, the coupling is very important. Now, suppose the surface is something like this and you are putting your sensor here. So, this is the air gap, and we know that we want to actually measure the elastic wave. So, if there is a air gap available, then problem is that air gap will actually consume some of the energy, or it will actually not able to transfer the same energy to the piezoelectric element which is measuring this particular part. So, by that way you have to make sure that there is a firm coupling between the workpiece and the sensor, and sometimes people are using different type of glue, so that all the, even if there is some gap, this gap is filled by this glue and there is no any air gap available. Or you have to do some type of sample preparation before you apply some type of this acoustic emission sensor there. You clean it completely, then make sure that there are no any type of waviness available or the roughness at a high level, and then you do different type of operations. So, this is about everything about today's lecture. We will continue this topic further in the next class. Thank you very much.